Hello dear friends, welcome once more to another video in our YouTube channel. In this video friends, we shall be looking at the correction of the Cameroon Advanced Level Physics, the June 2025 guys, Physics Section A. So friends, we shall be looking at the complete correction of this particular section, which there are 5 questions and you want to answer for a maximum of an hour. So friends, before I get started, my name is Macarius guys, and I'm your host for this channel today. Make sure you like the video friends, because the like actually motivates me to keep on creating more great content for you friends. If you have a worry friends, please leave it in the comment section down below so I can get back to you to make you understand so well as soon as possible. Okay friends, let's get started. The question 1 reads that the specific charge delta of an ion that is accelerated through a potential difference U into a uniform magnetic field B is given as delta equal to 2U over B squared R squared, where R is the radius of the circular path of the ion in the magnetic field. We should show that this equation is homogeneous. Okay, so friends, I think all of us must have studied this particular concepts in A-level chemistry, right? That is a concept of homogeneity. But now friends, we know for sure that if an equation is homogeneous friends, it means that all the terms in that equation should have the same base unit, right? Okay, let's get started friends. That's the equation that we have. So friends, generally, if the equation delta equal to 2U over B squared R squared is homogeneous, it ever means that the units of delta has to be equal to the units of 2U over B squared R squared. Now guys, the units of R squared, let's start with the things we know. Since they said R is simply the radius, so the unit of R is meters. Therefore means the unit of R squared has to be meters squared. We simply square the units. Then our friends, we know for sure that since they said U is a potential difference, right? And we know from our formula U equal to work done over charge, that is potential difference equals work done over charge. It means that friends, the unit of U has to be equals to the unit of work done friends is Newton meters, that of charge is in coulombs. But friends, the newtons and the coulombs friends are not base units in the SI unit system. They are not friends, so we have to convert them onto their base unit. So friends, we know that the newtons can be given as kilograms meters per second squared. Then we have the meters. Then the coulomb friends is given as amperes times seconds. So if we replace here with amperes seconds and the newton with kilogram meters per second squared friends, and we simplify, we have kilograms meters squared per second cube per amperes. Now friends, we also know for sure that the force F on its current I carrying conductor of length L in a magnetic field of strength B such that it is at right angles is related by the equation F equal to BIL. So friends, our goal of using this formula is simply to get the units of B, which they said B is simply the magnetic field strength. Now friends, you discover that I simply made some short statement before writing the formula down, right? That is to tell you that formulas in physics friends are not valid when their symbols have not been defined. So once we've defined all the symbols here, we are now permitted to use this formula. Okay, so friends, at this point now, if we make B the subject and take the units on both sides, we are going to have the units of B to be the same as the units of F over IL. But friends, the units of F is kilograms meters per second squared. Then that of I is a current, L is simply in meters. So if we simplify friends, we are going to have kilograms per ampere per second squared. Great. Now guys, we can simply say that now our units of 2U over B squared R squared simply becomes, note friends that 2 is simply a unitless constant, so it has no unit or its unit is 1. Great. So we are going to have that of U, we called it here to be kilograms meters squared per second per cubic seconds per amperes over, we have that of B squared. So friends, if the units of B is kilograms per ampere per second squared, it means the units of B squared is got by squaring all of these terms. If we square that, we are going to have have kilograms squared. Then we have per ampere squared. Then we have seconds to the power -4. Then rho squared becomes meters squared. If you simplify, friends, we have an answer of per kilograms, amperes, seconds. Now, friends, now that we have simply found the units of the right hand side, let's go ahead now to find the units of the left hand side. If they are the same, therefore means we can conclude that the equation is homogeneous. Now, friends, we know for sure that since they say that delta is the specific charge of an ion, we also know that, friends, the specific charge delta of an electron, which is the same as that of an ion, is related to the charge E and the mass small m by the equation delta equals to E over m. It therefore means that, friends, the units of delta has to be the same like the units of E over m. We know that E is simply the charge, so it's in coulombs. That of m is in kilograms, since m is a mass. Now, friends, it therefore means that the units of our delta becomes that of E is the coulombs, which is simply amperes times seconds. Then that of m is the kilograms. So if we simplify, friends, we have the units of delta to be the same like kilograms, like to be the same like per kilograms, amperes, seconds. So, friends, we can say that the units of delta, which is equal to this, is equals the units of what? 2u over b squared rho squared, right? Which is the same as per kilograms, amperes, seconds. So, friends, we can simply conclude that hence the equation delta equal to 2u over b squared rho squared is homogeneous. Wait. So, friends, that's it. So, friends, before I continue, friends, if you've not subscribed to this channel, friends, please go ahead and subscribe to the channel, friends, because that's a method that you stay updated to all the contents we produce here. If you don't subscribe to the channel, friends, you will not be having notifications each time we upload new videos, guys. And once you subscribe, friends, please turn on your notifications so that each time we upload new videos, you shall be the first person to get notified. Okay. So, friends, that's how we can answer this first part. Now, the next part is saying that all correct equations must be homogeneous, but not all homogeneous equations are physically correct. Full stop. Using a stable example, explain the meaning of this statement. Okay. So, friends, let's take this question stepwise. There are two parts. The very first part is that they want us to explain the fact that all correct equations must be homogeneous. Now, friends, this first statement, friends, simply means that because all correct equations must be homogeneous, it means that this statement has to be true because all the terms of the equations will have the same base unit. Note, friends, note that if an equation is correct, we can say for sure that that equation is homogeneous. But, friends, the reverse of this statement is not true, or better say, friends, the converse of this statement is not true. Namely, if an equation is homogeneous, it means that it is correct. That is a false statement, friends, as we shall see. Okay, so, friends, this is simply the explanation of that first part, which is saying that all correct equations must be homogeneous. That's true, because that all the terms of the equations will have the same base unit. Now, let's look at the next part, friends. We shall have two answers to give for the next part. The next part now is simply saying that we should explain using stable examples what the meaning of this statement. Okay, for instance, friends, this example, the equation for kinetic energy Ke equals to 1/2 mv squared. This equation, friends, is homogeneous. Okay, is homogeneous. Now, but the statement not all homogeneous equations will be correct. This is simply what we want because, friends, of the presence of wrong unitless constants. Now, guys, if an equation is homogeneous, we cannot conclude that that equation is correct because homogeneity, friends, does not take care of wrong unitless constants. For example, friends, we have seen that the equation for kinetic energy K equal to 1/2 mv squared is correct, right? But now, if we replace the 1/2 with Ke equal to 3 mv squared, this equation, friends, is homogeneous but not correct because of the constant we have. Here we have 3, here we have 1/2. The best constant here is 1/2, but here is 3, which makes equation homogeneous but not correct. Now, friends, the second answer that I mentioned at this point was that you can simply say that homogeneity cannot also check for the value for missing term, because if an equation has more than 2 terms, when one term is missing, that equation simply becomes homogeneous but not correct. Okay. So friends, that's how you can answer this part. That's it, friends. If there's something you don't understand, friends, the comment section is free, friends. Friends, let me know in the comment section below the school in which you are attending. Let me know, friends, and if you plan to take the advanced level this year or next year. Just let me know, friends, so I can give you extra hints and tips that you can use to have your A grade in physics without even stress. Okay, friends, let's go to question 2, friends. Are you ready? Let's go. The question 2 reads that 75 grams of steam at 100 degrees Celsius are passed into a quantity of pure melting ice in an insulated calorimeter. If the heat given out by the steam in condensing to water at 100 degrees Celsius is just sufficient to melt the ice, calculate the A, mass of the ice, B, equilibrium temperature of the mixture in the calorimeter. So friends, please understand what is going on. We have been told that 75 grams of steam, that is steam at 100 degrees Celsius. We can imagine how hot that steam is, right? It is passed into a quantity of pure melting ice at 0 degrees Celsius. Friends, the question did not mention the temperature, but you should know that ice is always at 0 degrees Celsius. That's the pure melting ice is at 0 degrees Celsius. Now, we have been told that the heat given out by the steam in condensing to water at 100 degrees Celsius is enough to melt the ice. So friends, they want us to get the mass of the ice. Okay. Now, friends, this isn't a challenge because we know that the heat supplied by the ice, friends, by the steam, sorry, has to be equal to the heat that is used to melt the ice. Because we know for sure that the steam is at a very high temperature of 100 degrees Celsius, and once it has been passed on to pure melting ice, that ice now gains an amount of heat to melt because the ice has to melt. And we know that the energy that is needed by that ice to melt without a change in temperature, friends, is simply called the specific latent heat, or its, friends, if we don't care about the mass of the ice, it is simply the latent heat of fusion of the ice. Now, the amount of heat energy that that steam needs to give out in order to condense is simply called the latent heat of vaporization. So friends, if they've told us that the amount of heat energy given out by that steam is enough to cool that ice, it means we can say that the amount of heat energy given out by the steam, that is the mass of the steam times the latent heat of vaporization of the steam, has to be the same as the mass of the ice times the latent heat of fusion of the ice. Because, friends, the heat supplied by the steam, friends, is given as ms LV. Then heat used to melt the ice, friends, is the mass of the ice times the latent heat of fusion of the ice. At this point, friends, they want us to get the mass of the ice. If we make the mass of the ice the subject, and we plug in our values, friends, we are going to have Mi being equal to the mass of the steam, friends, is 75 grams. Under normal circumstance, friends, we have to change from grams to kilograms, but we don't care about that because we still want to have our answer in grams. Okay, we need to have our answer in grams, so we don't care that much about converting from grams to kilograms. But if you convert, friends, you are correct. Okay. If now, friends, according to your formula booklet, if you check the value for the latent heat of vaporization of your formula booklet, you will see that it is 2.26 times 10 raised to the power 6 joules per kilograms. Similarly, guys, if you look at the specific latent heat of fusion of ice in your book, in your formula booklet, you will see that it is 3.34 times 10 raised to the power 5 joules per kilogram. So if you simplify, friends, we have an answer of about 507 grams. That is, friends, this is to the nearest significant figure. If you look at what they've given us, guys, is everything is to the nearest whole number. Okay, so please respect that. Respect the significant figures, friends. Respect the way the values have been given. Okay, so friends, that is it. The next part, I want us to get the equilibrium temperature of the mixture. Now, friends, we know that when all the ice must have been converted to liquid, we can simply say at this point that, friends, the heat energy that was supplied to that ice has to be the same as the amount of energy that is needed to convert that ice to liquid and to raise the temperature of that liquid. Let's note, friends, that the ice simply melted at what? At constant temperature. That is why the specific latent heat of fusion in this case, friends, is independent of the change in temperature. So, friends, what am I saying? We can say that in accordance to this, the heat supplied by the steam, that is simply the mass of the steam, specific capacity of water, because steam is still in the liquid state. Once it has been converted, once it has melted ice, friends, both the steam and the ice becomes water. So you're going to have the mass of the steam times specific capacity of water. The steam initially was at a temperature of 100 degrees Celsius, right? When everything gets attains a uniform temperature, the change in temperature, friends, has to be given as 100 minus theta. Then, friends, has to be equal to the mass of the ice, specific capacity of water, into our theta. Because when that ice now receives some amount of temperature, initially it was at what? 0 degrees Celsius. So the change in temperature, friends, has to be given as theta minus 0 degrees. We have CW on both sides, they can cancel. If we now make our mi theta the subject, we are going to have this. If we now factorize and make theta the subject and simplify, plugging in the values, friends, we are going to have our theta to be the same as 100 times the mass of the steam, friends. We have the answer to be 75. Friends, we still keep our answer in grams, okay? We keep it in grams. Then, friends, the mass of the steam again is 75. The mass of the ice is, you notice that, friends, the answer we got here was 507, right? But this is simply the answer that was rounded up to the nearest whole number. But now, friends, we need a more accurate answer, okay? We need a more accurate answer, that is 507.49. This is at least more accurate than this. So, friends, if we simplify this, friends, we are going to have the equilibrium temperature theta to be the same as 13 degrees. So, friends, that is it. That's how we can answer this particular question. So, friends, it does make sense, okay? This answer simply definitely makes sense, because you know that the steam, look at the mass of the steam, friends, is 75, right? Then, friends, look at the mass of the ice that was there. So means we had more ice in that our calorimeter than steam. So means that this ice of this amount was enough to swallow up almost all the steam. Yeah. So that's why the temperature had to. So that's why if you look at the temperature, friend, the temperature has not changed that much, right? It hasn't changed that much, because from 0 degrees Celsius to 13 degrees Celsius is not much of a big change. So, friends, this answer makes sense. Okay. Now, the question 3 reads that figure 1 shows how 3 resistors, 3 batteries, and internal resistances and ammeters are connected in a network. Calculate Romans 1, the reading of the meters A, B, and C. Okay, now, friends, you notice that they've just given us a blank circuit. They've given us internal resistances, they've given us batteries, they've given us meters. But one thing we can simply say for sure is that the meter A, B, and C are simply ammeters, right? Because they're connected in series. So they are all ammeters. They have low resistances. Okay. Now, friends, the equation has not given us the direction of movement of current, right? The question hasn't given us how the current is moving, but that is for us now to improvise. We need to assign directions of current on our circuit. Now friends, we have to do that such that all the sources with very high values should be delivering current, while those with small values should be receiving current. Great. So friends, if you look at what we have, here, friends, you see that we have 9 volts, we have 3 volts, we have 11 volts. And note that current flows from positive to negative. So in this case, friends, this one that has the smallest value means our current has to be moving in a downward direction. There, friends, this one that has a higher value means the current has to be moving away from the positive terminal. Then this other that has a very high value, friends, current has to be moving away from the terminal as shown. Okay, so friends, at this point we need to apply the Kirchoff's current law, right? But now let's give values to this our current. Let's see that the current that is flowing through this metal A, friends, is I1, and this other flowing through this way is I2, and this other, friends, flowing through metal C is I3. It means that the region of metal A is simply I1, the region of metal B is simply I2, and that of metal C is I3. Great. So you need to define that. So friends, now according to the Kirchoff's current law, if we look at junction N, the Kirchoff current law is simply saying that the sum of the current entering a junction, friends, is equals to the sum of currents that are leaving that particular junction. So friends, what I'm simply saying is that the use that I1 is entering junction N, while I2 and I3 are moving out, right? So it means we can simply say that our I1 has to be the same as I2 plus I3. Let's call this equation 1. Now friends, what I'm about to do now, friends, is highly delicate. That's why I have made a video that is going to help you to master Kirchoff's law to your fingertips without even budging about any stress. So friends, at the end of this video, friends, I'll show you where you can view that video, but you can only view the video, friends, if you are online. Okay, that's the only way you can view the video, only when you are online. So friends, you have to stay online. If you've gone offline, friends, if you've downloaded the video, friends, you need to come back and watch online up to the last point before you can see the video that is going to teach you Kirchoff's law in an easy manner on screen displayed. Okay, now friends, let's continue. Now, if we consider our loop 1, let's call this to be loop 1, and in this direction, guys, we can say that we are going for the direction of flow of current, right? So at this direction, we can simply say that if we start from this point N, okay, we sum up all of these EMFs, friends, it should account to what? 0. Summing up all the EMFs and potential difference, friends, they should account to 0. So friends, if we start from this point, we are moving. When we arrive at this point, friends, there is an internal resistance at this point. The current is going upwards, so there has to be a negative potential. So there's a potential drop. If we arrive at this point, friends, the terminal at this point, we have touched the positive terminal last, so this has to be a positive potential. So if we do that, friends, we are going to have minus, the internal resistance here is 1 ohm, so 1 times the current flowing in this branch is simply I2, so we're going to have minus I2 plus 9. Then friends, the current is like this, minus 3 I2, because I2 is still flowing here. We have minus 3 I2. When we arrive at junction M, friends, we enter inside. We arrive at this, our 4 ohms. Which current flows in this branch is simply I1, right? So we are going to have minus 4 I1. We have minus 4 I1. Then we have minus 3 because we have touched the positive terminal first and touched the negative terminal last. So we are going to have minus 3. Then friends, minus 2 I1. That has to be equal to 0 since we've ended at the point where we started. If we simplify this, friends, we are going to have an answer of 2I2 plus 3I1 equal to 3. Let's call this equation 1. Now, friends, if we also apply our Kirchoff's voltage law on loop 2, going in this direction, friends, it means that similarly, we are going to have 3i1 plus 4i3 equal to 4. Let's call this equation 3. So friends, if this concept of a transversing loop is not that clear to you friends, make sure you watch this video online till the ending of this video, because at the end of this video friends, I have tagged a video that is going to help you to master Kirchoff's laws, how to use them to transverse loops friends. I can guarantee you that even if you've never studied Kirchoff's law friends, you understand so well friends, you understand it too well. Okay, now so friends, now that we have 3 equations in 3 unknowns, we can simply go ahead and solve, right? This is simply a case in which we have 3 equations in 3 unknowns. We can solve, we can just eliminate one variable and calculate the other. So friends, if we do you see that we have look at equation 2 friends, we have i1, we have i2, i1. Here we have the same i1 but i3. So let's remove i3 friends from the equation. So you discover that friends, if we substitute our equation 1 in equation 3, if we make i3 the subject and substitute in equation 3, we are going to have 3i1 plus 4i3 is what guys? Is i1 minus i2, right? Equal to 4. Simplifying that friends gives us 7i1 minus 4i2 equal to 4. Let's call that equation 4. At this point now friends, we can simply solve both equations, right? But friends, we may want to eliminate. Look at equation 4, look at equation 2. There is a 2i2, there's a 4i2. So if we multiply equation 2 by 2 and add it with equation 4 friends, you see that we are just going to have 13i1 equal to 10. Simplifying that friends, we are going to have i1 to be the same as 0.769 amperes. Now friends, solving for i2 is no big deal. Just simply carry i1 back to any of the equations to solve for i2. Once we have i2 now, we simply come back to equation 1. Since i2 is the sum of equation, since i1 is the sum of equation 1 and 3, we can still make i3 the subject and that becomes done. So friends, I won't do that friends, you all can do that. If you do that friends with me, you're going to have your i2 to be the same like 0.346. Doing that for i3, we have i3 to be the same like 0.423 amperes. So those are the values of i1 and i2 and i3. Okay, now the Roman 3 is saying that we should get a potential difference between m and n. Okay friends, that is between these 2 points, which is simply the sum of these ones in this branch O friends. It is simply going to be the sum of these other ones outside. That is in accordance to our Kirchoff's voltage law or the Kirchoff's loop law. So friends, to get this thing done, we can simply say that friends, if we start from here, summing this, we are going to have negative i2 plus 9 minus 3 i2, this then minus the potential difference minus v mn should give us 0. So friends, if we solve everything knowing the value of i2, we are going to have our v mn, that's the potential difference between m and n, to be the same as 9 minus 4 into i2 friends is 0.346, which means if your i2 was wrong, your vmn must be wrong. So simplifying that friends, we have our v or mn to be the same as 7.62 volts. That's it. Or you can run it up to the nearest whole number to be 8 volts friends. All right, so friends, that's it. The last part is saying that we should calculate the power dissipated as heat in the 5 ohm resistor. So friends, generally the power dissipated by a resistor is given as P equal to I squared R. If we plug in everything friends, our I, do you see that the current that is flowing through the 5 ohm resistor friends is simply I3? Is I3 not so? So it is I3. So we use the value for I3, that's 0.423. So we are going to have P equal to 0.423 squared times R is 5. Simplifying friends, we have the power dissipated to be the same as 0.89 watts. So friends, that's how we can answer question 2 and question 3 and score all the marks friends. Don't forget friends to subscribe to this channel friends. That is how you get updated Subscribe to this channel, friends, and stay updated, friends. I promise to make everybody to have an A grade in physics. I can only do so, friends, if you subscribe to this channel. We shall upload that for math, friends. Even the other section for this particular here, we shall upload in this channel. Just subscribe and stay updated. Okay, let's go to the next question, friends. Are you ready? I'm ready too, friends. Let's go. The question forwards that Figure 2 shows a cylindrical container holding a sample of an ideal gas of molar mass 0.024 kilograms at a pressure of 1.40 times 10 raised to the power 5 Newton meters per second, Newton per cubic meters, and temperature of 78 degrees Celsius. That's the setup. Then they are saying that what mass of gas is present in the container. Now, friends, according to the ideal gas equation, PV equal to nRT. So, friends, in this case, we know that our P is a pressure, V is a volume of the gas, which they said it is filled. So, it means that the volume of this, our gas, has to be the volume of this, our cylinder. Then R, friends, is simply the molar gas constant. N is the number of moles. And T is simply the absolute temperature, friends. The word absolute is highly, very, very important. It has to be the temperature in Kelvin, not in degrees Celsius. So, friends, in this case now, we can simply, so at this point now, friends, knowing that our N is the number of moles, that is given mass over molar mass. If we do that, friends, we are going to have our PV to be same like small m over big M. Small m is the mass in grams. Big M is simply the molar mass. R is, like I said, friends, the molar gas constant. T is the absolute temperature. If we make M the subject, friends, we're going to have M to be the same as PV M over RT. So, friends, you notice that we have the pressure P, right? We have the molar mass M. We have the Boltzmann, the R. R in this case, friends, the molar gas constant, which you can find out on our formula booklet. T is the temperature that has been given. So the only thing that we don't know here, friends, is simply V. That's the volume of the shape of the gas, which is simply the volume of this cylinder. But we can get it, friends, knowing that the volume of a cylinder in terms of its diameter is simply given as V equal to pi d squared over 4 times h. Knowing that we have these values in centimeters, which we must convert them to meters. So if we do that, friends, and substitute our values, we are going to have pi, the diameter is 2.5. Doing that to centimeters, we have 10 raised to the power negative 2. Putting that to meters, doing the same thing for our h, we have that over 4. Simplifying, friends, you have the volume to be same like 3.53 times 10 raised to the power negative 5 cubic meters. So, friends, I have respected the significant figures. I have respected the list here, friends. You can see 1.40. So I also have 3.5 something. That's the volume. Now, friends, if we now plug in everything now into this our formula, the pressure P is 1.4 times 10 raised to the power. That's putting everything, friends. The temperature here, friends, is 78 degrees Celsius. We have to convert that to Kelvin by adding 273. And simplifying, friends, we have the mass present of that in that cylinder to be M equal to 4.1 times 10 raised to the power negative 5 kilograms per cubic times 10 raised to the power negative 5 kilograms. Great. So, friends, this is the mass present in that cylinder. Now, the next part is saying that how many molecules of the gas are present. So, friends, how do we get that? We should know that the number of molecules or the number of particles is given by the Avogadro's constant, given as N equals the number of moles times the Avogadro's constant. So, friends, means our N is ever going to be the number of moles, friends, is given as given mass over molar mass. The given mass, friends, is what we calculated to be 4.1 times this. But, friends, this is an approximate answer. Okay, we need to get the exact answer. This one is more accurate. So we are going to have 4.0644 times 10 raised to the power negative 5. The molar mass is 0.024 kilograms. Avogadro's constant is 6.02 times 10 raised to the power 23rd. So, friends, if we simplifying this so well, we have an answer of 1.02 times 10 raised to the power 21 molecules. So these are the number of molecules that are present in that cylinder. Quite large, right? Okay. Now the last part is saying that we should calculate the average kinetic energy of the gas molecules. Now friends, this is the first time that I've seen the GC board bringing for the formula equation that needs this formula. But we should not forget that according to the kinetic theory of gases, it is simply saying that the average translational kinetic energy, friends, is related to the absolute temperature and the Boltzmann's constant by the temperature by the formula Ke equal to 3 over 2 kT, where K is the Boltzmann's constant, T is simply the absolute temperature. So in this case, friends, if we plug in everything, guys, we're going to have 3 over 2. The Boltzmann's constant from the formula booklet is given as 1.38 times 10 raised to the power negative 23rd. The absolute temperature, friends, is 351 Kelvin. Simplifying, guys, we have 7.27 times 10 raised to the power negative 21 joules. So friends, that is the kinetic energy. Okay friends, that's it for this question. Let's go to the last part, friends. Are you ready? I'm ready too. Let's go. So friends, the last part is simply based on quantum physics, the experimental observations of the photoelectric effect. So now the question 5 reads that state 2 experimental results of the photoelectric effect which cannot be explained by the classical wave theory and explain them using the quantum theorem. Okay, now friends, let's since the question wants us to list and explain, the best way for us to do that, friends, is to use the table format. Let's insert our table of this form. Here we have the experimental observations, here we have the quantum explanations. Now friends, the very first observation that was observed is that the emission of photoelectrons, friends, is instantaneous. That is the moment that light of that frequency hits the metal surface, friends, photoelectrons starts being emitted immediately. Now friends, this was an issue with the classical wave theorem. It was an issue because they never expected that. They expected that the metal should at least absorb some amount of light before electrons can be emitted. But contrary to what the quantum theory states, it is simply saying that, friends, the moment that the frequency of light hits that surface, that metal surface, friends, electrons will be emitted instantly, immediately. So friends, the quantum explanation is simply saying that, friends, a single photon is enough to emit one electron. So which means that whenever we irradiate that metal surface with light of that sufficient frequency, friends, it means that the moment one photon lands on that surface, it is enough to release one electron. Great. That's it, friends. That's what the quantum theory explained about. So now the next one, friends, is simply saying that emission only takes place, friends, if the frequency of the incident radiation is greater than the threshold frequency. But now, friends, the wave theory, the classical wave theory, friends, did not actually see this to be meaningful because they think that even if there is no threshold frequency, no matter the frequency of light used, the metal surface should absorb some amount of heat, or the light should heat up the surface before electrons can be emitted. But the issue now is that, friends, no matter how intense that particular light is, so long as the frequency is not above the threshold frequency, friends, electrons will never get emitted no matter how long you irradiate them. So friends, what the quantum theory was simply saying that a photon in a low frequency light beam, friends, has energy that is too small to release an electron. Great. So there is that minimum frequency that the light beam has to reach before electrons can be emitted. And that frequency, friends, is known as the threshold frequency. Now, the very last one is simply saying that, friends, the maximum kinetic energy of the photoelectron is independent of the intensity of the incident radiation, but proportional to its frequency. So, friends, what am I saying? What are we saying here? We are simply saying that the intensity of light does not even alter the kinetic energy of those electrons, because the intensity of that light, friends, simply affects but the number of electrons emitted per unit time, okay, which is proportional to the intensity of the radiation. So friends, the quantum explanation simply suggests that greater intensity, friends, does not mean that the photons are more energetic. So friends, the electrons cannot have more energy. They all have a maximum energy, in which, friends, increasing the intensity of that light rays of that light, friends, will not alter the kinetic energy, but it will rather increase the amount of electrons emitted per unit time. Okay, so friends, that is it. So friends, that's it. These are the observations, these are the quantum explanations. Now the next part is saying that the ionization energy of mercury is 10.4 electron volts. You should calculate the maximum wavelength required by the incident radiation to emit an electron from a mercury atom. Okay, friends, we know that the energy of the mercury atom is given as E equal to hf, where h is the Planck's constant, and f, friends, is simply the frequency of the ionized frequency of the incident radiation. We also know that according to the speed of light in vacuum, the formula of the speed of light in vacuum, which is related to its frequency and wavelength, if we make our f the subject, we have f to be same like c over lambda. Substituting our f here, friends, we are going to have our E to be the same as hc over lambda. Making lambda the subject, friends, we have lambda to be same like hc over E. Plugging everything, friends, the Planck's constant is given as 6.63, or you can say 6.626. That's per the formula booklet. Times 10 raised to the power negative 34 joules seconds. The speed of light in vacuum is 3 times 10 raised to the power 8. Then now the energy, friends, has been given us in electron volts, which you must convert that to joules. The electron volt, friends, has a value of the charge of an electron, friends, has a value of 1.6 times 10 raised to the power negative 19. So we multiply it by 10.4, and simplifying, friends, we have an answer of lambda equal to 1.195 times 10 raised to the power negative 7 meters, which, if you respect significant figures, friends, you just have 1.2 times 10 raised to the power negative 7 meters. Or, friends, more formally, maybe we can decide to say that this is going to be 12.0 micrometers. So, friends, that is the answer. That is it. So, friends, as you can see, friends, we have simply finished this section A. Friends, if there's something you think about this question, friends, the comment section is free. So, friends, check the link, check the description of this video. You shall see the link that is going to channel you to the video that is going to show you how I taught students the Kirchoff's voltage and Kirchoff's current law, how to apply it easily without even stressing. So, friends, that's it for the video. That's it. The video on screen now, friends, as you can see, is going to show you how to do that for Kirchoff's law. That is going to teach you Kirchoff's law, friends, in a practical and exciting manner, friends. Please check it out, friends. As always, don't forget to subscribe to the channel, friends. I am Omenjo Macarius, friends. Have a blessed day.